Hello everyone and welcome back to the class of fundamentals of particle and fluid solid processing. Today we will start our discussion on particle size enlargement. We have seen a relatively detailed discussion on the particle size reduction. Now we will see that why enlargement is also important. So, size enlargement, by its name you can understand it is the formation of larger masses from smaller particles by keeping this identity of the original particles intact. So, it is basically a formation of agglomeration. Say, it is a vital step in various process industries and particularly it finds extensive application in pharmaceutical, agriculture and food industry. It is also used in several other industries as well, like in minerals, metallurgy and ceramic industries. So, where basically we have already finer particles or fine particles, but we need some agglomerates. And why is so? Because by doing so we can reduce the hazards that is associated with the fine particles, for example the dust hazard, its safety hazard or health hazard related to the fine particles, because one of the most detrimental dust for our human respiration is the asbestos. Now, it's the size distribution, is the size particularly that is detrimental for our lungs. So, it is the finer size of the asbestos that is actually very dangerous for our health. It also reduces the chances when we make these smaller particles together, we combine them, we bind them, it also reduces this caking and lump formation tendency when these are together. So, basically say some fine particles, you have a bulk of fine particles that you intend to flow. It is not easy to make them flow. Instead, if you had some aggregates of these smaller particles, it can roll over very quickly. So, which means by enlarging its size, we also improve its flowability or the flow property. We increase the bulk density for its storage. Also, by increasing this size of a particles in terms of aggregates or granules, we control the use of active ingredients in there, which is very much helpful in the drug industries or the pharmaceutical industries. And also, when we have a reasonably bigger size than the ultrafine particle or say the fine particles, it helps us to have a control over the surface to volume ratio or the specific surface area. Now, the importance of these we have also already seen in the last classes. So, not only the size reduction is important, size enlargement is equally important in several industries. And the one of the foremost reasons is the reduction of dust hazard or the health hazard with the fine particles. The second most important, I would say, is the improvement of its flowability. So, all these reasons leads to discussing this topic, that why size enlargement and how it is done. So, agglomeration that I am mentioning is the formation of agglomerates or say the aggregates of smaller particles. Now, granulation is a strategy of this agglomeration by agitation methods. there are several methods of enlarging sizes, like the granulation, drilling operations. There are other operations we will mention in due time, but let us focus primarily here on the granulation because of its very common use or extensive use. Like we have only chosen ball mill in the case of size reducing equipment and has seen its details. Similarly, here we will take this granulation operation as one of the size enlargement process. Although there are several processes, we will focus on this one mostly in this section, and we will see that what are the forces at the molecular level that is involved in this granulation process, or what are the forces that are dominant that this granulation process during this, what are the forces we have. So, for this what we will see the types of interparticle forces and their relative importance in the granulation process. There are different steps in this overall granulation process, like the wetting, growth, consolidation, attrition. These are the steps we will see in a brief details, and we will go in the brief overview of the industrial granulation equipment to complete our section. So, which means again, as a size enlargement process, we will mostly focus on granulation, which is agglomeration by agitation. We will see its various stages. We will look into the various molecular level forces that are important in having this granulation efficiently, and then at last we will have an overview of various granulation equipment that we did, like in case of size reduction. So, one of the most prominent and most talked about interparticle force, you know that it is van der Waals force. Van der Waals is the name of the scientist after which this force name is there. So, it is the molecular level attractive forces. This van der Waals forces is the forces that are attractive in nature at the molecular level. The energy level of these forces are in the order of 0.1 electron volt, which is roughly 1 electron volt is roughly equals to 1.6 into 10 to the power minus 19 joule, and this energy decreases with the sixth power of the distance between the molecules. It is the intermolecular forces, it is the attractive in nature, but this strength of this force decreases with the sixth power of the distance between the molecules. So, as you go far or distant from molecule to molecules, this force strength drastically decreases, but it is a relatively larger range force compared to the chemical bonds. Now, Hamaker estimated this attractive force or identified this force between a sphere and a plane surface. So, how or how much is the intensity of that force? So, if that force is F, this VB, van der Waals abbreviated form is VW, here we have mentioned, then that force he has related with a KH, which is a constant term called the Hamaker constant. R is the radius of the sphere, that is the attraction between a spherical object and a plane surface, divided by the 6y square, where y is the gap between the sphere and the plane. This is of radius r. So, similarly, there are several expressions for this force between the two spherical object, two planar object. Different expressions are available. So the gist is that it is an attractive force. We have seen its strength in the order of 0.1 electron volt. These forces, it decreases rapidly as we increase the distance between two molecules, but it is still a long range force than the chemical bonds. The way of estimation of this force has been established, and that has been done by Hamaker, where this Kh is the Hamaker constant in this expression. So this is one of the major forces, molecular level forces that are there, which is relevant for this granulation process. The other relevant force is the forces due to adsorbed liquid layers. Now, the layer of, say, when there is a presence of vapor near the particles, then the layer of absorbed vapor on the particle surfaces happens in presence of this condensable vapor. On the several, we have, say, a bunch of particles are there, and in presence of this condensable vapor we have a layer of adsorbed vapor on the particle surface. Now this overlapping of this adsorbed layer results into some kind of bonding forces. Now overall strength of these forces depends on the area of contact and its tensile strength. Its thickness and the strength of these layers increase with increasing partial pressure of the surrounding vapor. And beyond a critical pressure, this adsorbed layer bonding is superseded by the liquid bridge bonding. These layers then forms the liquid bridges between the particles or the molecules. So if we have a bunch of particles surrounded by condensable vapor, the particle surface adsorbs that vapor and results into a adsorbed layer of that liquid, and this results in bonding force, because then if these particles are in contact, this adsorbed layer basically forms a bridge between these two. So the bonding strength of these forces are dictated by the area of contact and its tensile strength. The thickness of this adsorbed layer and its strength, it increases with the increasing partial pressure of the surrounding vapor. And beyond a critical pressure, this absorbed layer forms the liquid bridges. Now, as we have introduced now the liquid bridges, this basically happens in presence of any minuscule amount of liquid, say on the particle surface. It actually alters the interparticle forces. So presence of any minuscule amount or a very small amount of water or liquid on the particle surface alters the interparticle forces, because what it does, it actually smoothen the particle roughness effect. It smoothen the particle, the surface imperfections. So it increases the particle-particle contact and reduces the interparticle distance. But if we have the presence of sufficient amount of liquid on the particle surface, then the earlier discussed forces, the magnitude of that is not taken into further consideration. It becomes insignificant. Then what happens? It forms the liquid bridges. Now, various stages or states of this liquid bridges has been identified by researchers, and those have been categorized based on the saturation of the interparticle pores by the liquid phase. We have seen or heard about the term called the porosity or the voidage. Now, interparticle pores or the space, we say the voidage or the porosity. Now, the saturation is the filling up of those pores by the liquid phase or by the liquid. Now, based on the level of saturation, we have different state of this liquid bridges, starting from pendular, funicular, capillary, and the droplet. This has been identified by the researchers. So, what are those stages, and what happens there, how it looks like? So, this is the state we call the pendular stage or the pendular state. Now, what happens here? Liquid is basically retained as a point contact in between the particles, okay, in the form of a liquid bridge. So, these are, say, the particles, these empty circles, and in between we have the point contact of the liquid which acts as a liquid bridge. So, liquid is basically stuck in between these two particles, which in fact act as a binder. So, in case of pendular state, these bridges are all separate and independent because of very low saturation of the or low amount of liquid present in the voidage or interstices. The presence of this minimum amount of liquid that forms the bridge or forms the point of contact, that results in the surface tension forces which binds the particle. This liquid surface tension force actually binds the particles, and since the bridge is formed, there is a curvature of this surface, this liquid surface, which results in the capillary pressure, and the capillary pressure is measured as the surface tension multiplied by 1 minus R1 minus 1 by R1 minus 1 by R2, where R1 and R2 are the radii of the curvature of these surfaces, and this is the surface tension. So, when the pressure in this liquid bridge is less than the ambient pressure, then this capillary pressure and the surface tension force becomes additive. This together becomes the total resulting force. So, this is the initial stage of the, say, granulation or this formation of the liquid bridge. Now, why this is important we will see later in granulation. So, here What is the stage? That if we have an amount of liquid that is present in the surface the cluster of the particles, the voidage or the interstices, the pores are initially filled with the liquid, and how it fills or what are the amount of liquid, that dictates all these stages. So, minimum amount of liquid, point contact between the particles is the pendular state, where we can identify the each and every bridges separately. As the amount of liquid is increased, there will be some free water that can move, or the free movement of liquid whenever it is present, it moves to the funicular structure or funicular state, and that reduces in the attractive force between the particles. With further increment in the amount of liquid, we move to the capillary state, and on enhancing the liquid amount further, we get the droplet state. So, basically you can think of this transition of one state to other in forming the liquid bridges is the saturation of the void spaces. The amount of liquid that are present in the pores of the particle, interparticle pores. So, as we increase the amount of liquid, it completely fills the interstitial pores, resulting in the capillary state. The granule strength decreases due to there are now fewer curved surfaces. So, the capillary pressure and all these are only the important, fewer boundaries are there that were responsible for the surface tension forces. So, as you increase the liquid amount, it becomes in the capillary state. You further increase the liquid amount, it goes to the droplet state. Now, in the droplet state, particle is completely dispersed in the liquid. So, quite obviously the strength of having of this bond of these forces is very low. So, it has been seen that increase in the amount of liquid in its pendular state has a small effect of the influence on the strength until it moves to the funicular state. So, if it is not in the funicular stage and it is in the pendular state, you increase the amount of fluid in the pendular state, it increases the bond resistance to rupture. But as it moves to the funicular stage, the strength decreases. Now, this pendular bridge yields in strong granules, because this state, if it is followed in the granulation, it results in strong granules, because the amount of liquid is not what the critical condition, provided it should not transit to the funicular or capillary region. The amount of water in the pendular state is not very critical until and unless it reaches the funicular or the capillary region, because increasing the amount of liquid in the pendular stage until a critical point increases the bond resistance to rupture. So, therefore, it finds relevance in the granulation process, because in granulation what we try to achieve is that fine particles or smaller particles and its agglomeration using agitation as sturdy as possible. That aggregate should be able to withstand certain amount of attrition or external forces in order to not break again. So that means, as I mentioned, you can think of this transition from one regime or one state to the other state as a function of saturation of the liquid phase. So such saturation can also be increased by reducing the voidage or the porosity, or the moving the particles closer together, which is called the densifying operation, or concentrating the whole particles together. So, and that is why we have seen these steps in terms of the forces that are acting for the liquid bridges. So, which means we have now introduced in this class is that the difference of intermolecular forces or the molecular level forces that are relevant for the granulation operation. The reason we have choose only granulation to focus on for the time being is that is its extensive application, is its popularity. We will continue this discussion on the different molecular level forces, different surface forces in the next class, because there are a couple of forces that are left before I discuss its relative importance, how these forces are comparable in terms of particle size, or when these forces to be considered in which stage. Before that, we have to go for we have to see the what are the forces are there, what are the relevant forces are there. So we will continue this discussion in the next class as well, and till then, thank you for your attention.